Today in the workshop, we're working with Hall effect switches and stepper motors. We'll see how Hall effect switches work and how to use them as both limit switches and homing sensors. It's a magnetic episode today, so welcome to the workshop. Hello and welcome to the workshop. Today we're back with working with stepper motors. Now we've worked with stepper motors a number of times before, so if you're not familiar with steppers, please check out one of the earlier videos where I'll explain exactly how they work. But as a basic summary, a stepper motor is a motor that is moved in individual steps. And by using a technique called microstepping, those little steps can actually be a fraction of a degree. If you couple an arrangement like that with some gearing, you can move something down to sub-millimeter accuracy, and this is why stepper motors are used in applications like printers and CD and DVD drives, because they need to move ahead to a very, very accurate position. Now, stepper motors are wonderful. We're going to use them in a lot of our robotics projects, but one thing about a stepper is when you first power it on, you have no idea where the actual shaft is located. You need to find that out, and for that, a lot of systems use something called a homing system. They'll rotate the shaft or move the mechanism until a homing sensor is activated. Then the stepper knows what position it's in and it can act accordingly. Another common application is something called a limit switch. This is where you put switches at one or both ends of the travel of the device that you're driving with the stepper motor. And when those switches are activated, the stepper motor knows that it's reached the end of its travel and it can act accordingly, either stop or reverse, however you've designed your product to work. Now, these switches can be a number of different types of switches. You can certainly use conventional switches. In fact, micro switches are used quite often for these kind of purposes. And conventional switches, of course, are very easy to work with. But they have their problems. There are a lot of environments, dirty environments, or environments where they might get wet, in which they're not suitable. Also, depending on the arrangement you have with them, they can go off mechanically, and so the homing position or the limit switch will not be in the correct position. However, they still can be used in these applications. Keep in mind they have a lifespan because of the number of times you're switching them as well. Now, another common type of switch used for limit and homing is an optical source sensor. And we've used optical source sensors before, such as when we used the rotary encoders for those little car motors. Optical source sensors are just as they would dictate an optical source, which is generally an infrared LED, and an infrared receiver on the other side. And there's a gap between the two, and if something enters the gap, it'll break the light beam and thus trigger the sensor. Now, this is very commonly used, by the way, on printers. They usually have a little tab that's on the shaft of the belt that drives the print head, and when that tab goes in between an optical source sensor, it knows it's reached its homing position. But we're not going to use either of those types of switches today, although you can certainly modify the designs I'm showing you today to use them. What we're going to use is something called a Hall effect switch. Now, Hall effect switches and Hall effect sensors respond to magnetism. They can measure the intensity of the magnetism. They can also measure the magnetic polarity of them. They're semiconductor devices, and they can be used in all sorts of environments. So if you have a dusty or a dirty environment, something which a mechanical or even an optical switch might get interfered with, you could use a Hall effect switch. And so what we're going to do today is we're going to start off by learning about Hall effect switches. There is a number of different types, so I'll go over that. We'll do an experiment to show you how to work with Hall effect switches, and then we'll add an Arduino and then finally some stepper motors in so we can build ourselves both a homing and a limit system. So once again, we got a lot to cover. Let's start off and learn a bit about Hall effect switches. Let's take a look at Hall effect sensors. Hall effect sensors respond to magnetic fields. The sensor produces a voltage difference across an electrical conductor. The magnetic field is perpendicular to the flow of the current in the Hall effect sensor. The Hall effect was discovered by Edwin Hall in 1879. Modern Hall effect sensors and switches, of course, use semiconductors. Hall effect sensors can be used both as magnetic field sensors and as switches. Hall sensors can measure DC current flow without actually connecting to the DC current. They're also used in automotive applications to replace the breaker points in vehicles. They can be used as electronic compasses. There are many types of Hall effect sensors and switches. The two most common types of switches are the latching and the non-latching switches. Now here's how a non-latching switch works. A magnet is brought near the sensor and the switch is activated. When the magnet is removed, the switch is deactivated. Now the magnet is brought closer, but because of the magnetic polarity, the switch is not activated. However, if the magnet comes in from the other side, it will activate the switch. Now let's look at the operation of a latching switch. When a magnet is brought near the switch, it is activated. When the magnet is moved away, it is still activated. Bring the magnet back, and it's still activated. However, if you reverse the polarity of the magnet, you can unlatch the switch. Hall effect switches and sensors are available in modules or as individual semiconductors. Either way, the connections to the Hall effect switch is very, very simple. There's a ground connection, a connection labeled S, which is the output, and a VCC, which is the positive voltage. Please note the order of these connections will differ depending on the device. So now let's start using our Hall effect sensors. So now that we know a little bit more about Hall effect sensors and Hall effect switches, let's take a look at some actual devices and see how they work. Now I've got two types of them here. I've got in my parts drawer a couple of different types. I've got an AH1815, which is this one over here, and this is just a basic Hall effect switch. And I've got a US1881, which is this one over here. It looks identical, but this is a latching switch. Now I've also got some modules over here. These two are regular Hall effect switches again on modules, and this is a latching one. The nice thing about these modules is they already have the pull-up resistor on them, at least they do on the regular ones, and they've also got some LEDs so you can display the status of it without anything external. And so with that in mind, I've hooked a couple of them up over here on a solderless breadboard. Now I'm using my 5-volt bench power supply, and this is the regular Hall effect switch module, and it's got a built-in LED. So all I've done is I've connected 5 volts and ground to it, and we'll just observe the LED when I bring the magnets close to it. Now this one here is the US1881. This is a latching switch. I've also added a 10K resistor. Amusingly, I had to put the resistor at the back because when I had it at the front, my magnets kept pulling it out of the solderless breadboard and ruining the experiment. But this is the latching one, and since it has no indicator, what I've done is I've attached a logic probe over here. Now I don't have the probe hooked up right now, and the reason is as follows. When I hook up the probe, it makes a sound. The logic probe makes a different tone for either a high or a low, and that's very convenient when you're troubleshooting, but very annoying when you're not doing anything with it. So we'll just leave that alone until it's time to use it. Now I've got some very powerful magnets. These things are actually kind of a nuisance. They attract everything. In fact, yesterday I went to film this and I couldn't because I lost the magnets. They'd attached themselves to one of my screwdrivers. It took me about an hour to figure out which one. But at any rate, we'll take these powerful magnets and bring it toward our Hall effect switch, and as you can hopefully see, the light comes on. Now if I turn them around and reverse the polarity, nothing happens. It has to come in the same way, but I can use the reverse polarity if I want to go in from the back. And so as you can see, the switch works. The magnet doesn't actually have to touch it, it just has to be in proximity of it, and it is sensitive to the magnetic polarity. Now let's take a look at the latching switch. So let's hook the noisy logic probe up, and the green light and this particular tone indicate that the signal is low right now. And so I'm going to bring my magnet near it. And as you can see, it's gone high. And I've taken the magnet away and it's still high. It is latched. I can bring the magnet back, it won't do anything. But if I turn the magnet around and bring it this way, the opposite polarity, it unlatches. And so that's the operation of a latching switch. And so there you go, the basic operation of Hall effect switches. So now that we know more about how Hall effect switches work, let's start using them with an Arduino. So what we're going to do now is grab an Arduino Uno, hook a Hall effect switch up to it, and we'll just write a simple sketch to see how it works. So let's go ahead and do that right now. So here's what we're going to need for our first experiment. We'll need an Arduino Uno, and we'll need a non-latching Hall effect switch module. You could also use an individual component if you want to put a pull-up resistor in yourself or use one of the internal pull-ups in the Arduino. Optionally, we can add an LED and a dropping resistor for the LED. Any value from 150 ohms to 470 would work. The LED is optional because we'll be connecting it to pin 13, which also has an onboard LED on the Arduino. We'll start by connecting the 5 volts from the Arduino to the plus input on our module. Please note that on my module this is the center pin. Then we'll take the ground connection and connect it to the minus terminal on the module. Finally, we'll take pin 3 of the Arduino and connect it to the S or output pin on our module. If you're wiring the LED, connect pin 13 through the dropping resistor to the anode of the LED, and then connect the cathode of the LED to the Arduino ground. And this completes the hookup for our first experiment. Alright, so here's our very simple Hall effect sensor demonstration sketch. And when I say very simple, I mean it. In fact, I believe this sketch to be even simpler than the Blink sketch. And there's really not much to it. We first of all define the connections to the Hall effect sensor and the LED on pins 3 and 13 respectively. And then we go right into the setup. We set the LED as an output and the Hall effect sensor as an input. And then we do a digital write to the LED and we set its value low. So the LED, when set low, will be off, and of course when set high it will be on. And the loop is about as simple as we can get. We're going to do a digital write to the LED of the inverse of the value of the Hall effect sensor. And the reason we're using the inverse with the exclamation mark at the beginning here is that the Hall effect sensor is active low, so it's going to stay high until it detects something and then it will go low. So we want to send the opposite value of that to the LED. When the Hall goes low, we want the LED to go high. And so that's why we're doing an inverse. But other than that, this is extremely basic, and so let's hook it up and see what happens. And so here's our basic Hall effect sensor demonstration with the Arduino. Now this is quite simple really. This is the same Hall effect sensor module that I used in the earlier demo without the Arduino. I've added my LED and dropping resistor over here, and of course the Arduino is there, and the connections to the Hall effect sensor and the LED over here, and the power from the Arduino. So the Arduino's already running the sketch, and I've got my magnet, and it's going to operate pretty well as you might expect. When I bring the magnet near the sensor, you can see it lights the LED. You can also probably see the onboard LED on the Arduino's lighting too, so you don't even really need the external one, but it's easier to see in the video. Now this of course is a very simple demonstration and a complete waste of an Arduino. You could do the same thing by attaching a transistor to the output of this and driving the LED accordingly like that. But it does show you how you can interface a Hall effect sensor with an Arduino, and of course after that you can do whatever you need to do in software. Certainly something more exciting than just lighting an LED. You could pretty well control anything as you could with any switch. So now that you've seen that, let's move on to something a little bit more exciting. Okay, now we've seen how we can hook a Hall effect sensor up to an Arduino. It's time to add a stepper motor in. Now I'm going to use this motor. It's a small NEMA 17 stepper, very easy to use, but you could use any size stepper that you wanted as long as you gave it a suitable driver. For example, in a previous video I worked with a big stepper motor, and you could use that one as well. So we're going to start off by working with limit switches, switches that can limit the rotation of the stepper from one end to the other. Keep in mind that in real life operation you probably won't attach the limit switches directly to the motor, but instead you would attach them to the device you're driving with the motor. But in my demo I'm just going to attach them to the motor. So let's go ahead and look at implementing limit switches with Hall effect sensors. We're going to be driving our stepper motor with an A4988 module, and while we've used these modules before, I thought it would be a good idea just to briefly go over the connections on the module. Now the first two are VMOT and ground. Now VMOT is the voltage supply for the stepper motor itself, and ground of course is the ground from that supply. The 2B, 2A, 1A, and 1B connections are the connections to the coils of the stepper motor itself. Make sure to observe the polarity correctly, the polarity being indicated by the A's and the B's. VDD and ground are connections to the logic supply, the 5 volts that we'll be using for the module. The enable line is an active low line, and it's already been held low, so unless you pull this high, you can just leave it disconnected. MS1, MS2, and MS3 determine the microstepping mode of the module. Now the module does not microstep with any of these disconnected, but as you can see through this chart, you can change that mode if you wish to get a finer tuning on the stepping of your stepper motor. Reset and sleep are both active low. If they're pulled low, the module will either be reset or be put to sleep. Generally, in most operations, you tie these two pins together. The next pin is the step pin. This is where the pulses are sent in order to actually step the stepper motor. And finally, the dir pin determines the direction that the motor will rotate in. Now we're going to start off this experiment using the same hookup that we used for the last one. We've removed the LED and the resistor from it. We're going to add the A4988 module, a stepper motor, another sensor, a power supply for the stepper motor. We'll start by connecting the 5 volts to the positive connection on our second module. We'll then connect the ground to the negative connection, and we'll connect the output or the S pin to pin 2 of our Arduino. Now we'll connect pin 10 of our Arduino to the dir pin on the A4988 module. Pin 11 will be connected to the step pin. We're going to tie the sleep and the reset pins together, and then we'll connect our power supply for the stepper motor. Next, we'll connect the stepper motor itself. Please note the connections on your stepper motor and determine which ones you need to use for the 4 pins over here. And then we will connect the power to the A4988, the 5 volts from the Arduino and its ground. And this completes the connections. So now let's do our experiments. Now this is a sketch that we're going to be using to demonstrate the limit switch operation. It's also a pretty simple sketch. Now we start off by defining connections. These are the connections to the 2 Hall sensors. We're going to call them sensor underscore A and underscore B, and they go to pins 2 and 3. And then the dir and the step inputs on the A49988 are going to pins 10 and 11 respectively. Now you can use any 2 pins you want to. There's no consideration for PWM in this sketch because we are stepping the motor manually. Now these variables over here, PD is the pulse duration, this is the duration of the step, and this is in microseconds, it's the delay period. And so if you want to change the speed of the motor, you can go and change that value. And we also have a boolean called set dir, and that is defined as being low right now, and that's just the direction that the motor is going to be going in, and so we can flip that to change the motor direction. Now we have 2 interrupt handlers, one for each one of the 2 sensors, and right now I've got both interrupt handlers doing the same thing, but that's not a requirement. You could do something different, you could stop the motor, you could do something else, but all I'm doing is reversing the motor, and so I'm just inverting the value of set dir over here. And again, I've got them both doing identical tasks, but you don't need to do that. Certainly you could stop on one end and reverse on the other end if you wished. Now we go into the setup, and it's also very simple. We set the two outputs that are going to the A49988, and they're set up as outputs during step. And then the inputs from the Hall effect sensors, they're set as inputs, and we'll attach those interrupts to the two pins. So sensor A is attached to the limit underscore A interrupt, and B to limit underscore B. And remember that the Hall effect sensor is active low, so we're going to catch this on the falling end of a pulse when it decides to drop from high to low. Now the loop is very, very simple. All we are doing is reading the current value of set dir and writing that to the dir pin so we can control the direction of the motor. And then we're going to manually step it. So we're going to send the step output high. We're going to delay for the amount of microseconds determined by the variable PD. And then we're going to set it low, delay it by the same amount, and just repeat the loop. So the motor will keep on going until an interrupt occurs, and then after that the interrupt handler will just simply reverse the direction. So this will just go back and forth. So now that you've seen the sketch, let's go and take a look at it working. Now here's my limit switch demonstration setup, so let me show you what I've got over here. We've got a NEMA 17 motor mounted on a bracket on this block of wood over here, and on top of these two blocks of woods I've got a small solderless breadboard with a Hall effect sensor module on it, and of course that's wired down over here to my Arduino. Now the connections from the stepper motor are going to this little piece of perf board that I wired up. I wired this up sort of as a permanent adapter type of a thing. I used a JST connector, and then I brought it out to both a male and a female set of DuPont pins, and of course I can use the female ones identically to the female ones in the Arduino Uno, so I can plug my test leads into it. I also could plug test leads into the male ones if I used female leads, but I thought these would also be good in case I wanted to either run a DuPont cable to adapt the JST to the DuPont, or to have some test points. And I don't only mean for this experiment, I can use this in future experiments with this stepper motor as well. Now down over here I've got my A49988, and one thing that the observant on you might notice is I've added a capacitor on here that I didn't show in the schematic earlier. I'm sorry about that. It was a sort of an afterthought. In many A4988 designs you use a 100 microfarad capacitor across a 12 volt line. I think that's just so it can store a little bit of energy because of the energy that the stepper motor requires. And so the top line on this breadboard here is the 12 volts, and the bottom line is the 5 volts from the Arduino. Now the Arduino's all powered up and ready to go. It's actually running the sketch right now, but I don't have the 12 volts hooked up yet. This is the 12 volts from my bench power supply. So let's go do that and watch the limit switch demo. And as you can see, it goes back and forth. And a pretty simple demonstration. As I said earlier, you could do something other than reverse the motor when it hits a limit if you wished, and you could do something different with, of course, each one of the limit switches. Or if you just wanted to build your own set of windshield wipers, I think you've got a pretty good arrangement over here for that. So there you go. So now that we've seen how we can implement limit switches, let's move on to a homing sensor. Now a homing sensor would be used in a situation where you want to establish a reference point for the position of your stepper motor shaft, and from that point on you can actually calculate exactly how to move in very precise increments. So what we're going to do is we're going to just take one sensor right now and show you how you can implement a homing system with it. So let's go ahead and do that. Now here's the homing switch demo sketch. Again, this is pretty simple. Now what we do is we start off by defining connections as we did before. We only have one Hall sensor on pin 3 and the same two connections we're making to the A49988 on pins 10 and 11. We use the same variable to indicate the direction of our motor. Now we're not going to manipulate that variable in this experiment, but it's always good to have a variable that represents the motor direction, and we're going to set it low. Of course, if you wanted to, you could just set it high and it would simply go in the other direction. And then I've created a function called home function, which is the function for homing the motor. Now inside there I use a variable that represents the pulse duration, and I've set it to 4000, so if you want to change the speed that it homes at, just change this variable over here. And then I go into a while loop, and while I get a digital read of the Hall sensor equaling 1, I go through and run the same routine we had in the last sketch in order to step the motor. Now remember, the Hall sensor is active low, so if it's equaling 1, it's not detecting anything. So we just keep stepping the motor until finally we get a value of 0. And once we do, the Hall effect sensor will have triggered and we are going to move out of the while loop and end the function. Okay, now in the setup is where all the action happens in this script, and we basically go pin mode to set the pin modes for the A49988 and also as inputs for the Hall effect sensor. And then we simply call the home function. And so what will happen is we'll start our sketch up and it will home the motor, and then it will exit the setup and go into the loop. And I don't even have any code in my loop, but in a practical application, this is where you would put the code in order to move the motor or to wait for instructions or do whatever your project does. But you've now homed the motor in the setup. You know where the motor shaft is. So having seen that code, let's go take a look at it in action. And so here's our homing sensor demonstration, which of course is an identical setup to the limit switch demo, only in this case it is only this particular Hall effect sensor that is being used. So this is the homing sensor. The other one is still wired up and active, but of course it isn't being used in the program, so its input is just going to be ignored. Now I've got the sketch loaded up onto my Arduino, which is powered up, but I do not have the 12-volt supply hooked up, so I'm going to hook it up and then reset it so we can see if we can get it to home. It'll go through its setup routine and run the homing function. I'll press that. And there you go, it stops. And so now remember, you've now run through the setup and you're into the loop in your program. And so from this point you can do whatever you need to do. You can move the motor a certain number of steps, you can wait for commands, you can go through a sequence, but at least you know the exact position of your motor shaft. Alright, so that about wraps it up for today. I hope that you enjoyed the video and that you've learned something about using homing and limit switches with stepper motors and can start implementing those in your own designs. Now, if you'd like to get a hold of the sketches that I used today or get a bit more information about Hall effect switches and stepper motors, check out the article on the DronebotWorkshop.com website. You will find a link below the video right to that article and you'll get everything that you need. While you're on the website, please sign up for the newsletter if you haven't already. It's not a sales letter, just my way of keeping in touch with you and letting you know what's going on in the workshop. And if you'd like to discuss this a bit more, the best place to do that is on the DroneBot Workshop forum. You'll find a link to the forum below this video as well at forum.dronebotworkshop.com. Please join us. We've got a lot of great members on there and we have a lot of great conversations, and we can talk about stepper motors, Hall effect switches, or anything you like. So until we meet next time, please take care of yourselves, and I hope to see you again very soon here in the DroneBot Workshop. Goodbye for now.